Okay, let's give a try. Hmm? The question asked us, this question was given in mechanics 2003 AL paper, right? This is the first essay question given in that paper. Let me read the question, listen carefully. A space shuttle, when it stands on the launching pad, has a mass of 2 into 10 to the power 6 kilogram. The upward thrust means upward force in simple words. The upward thrust needed to move the shuttle is 3 into 10 to the power 7 Newton, which is achieved by, there should be a comma, which is achieved by burning 3 into 10 to the power 3 kilogram. 3 into 10 to the power 3 kilogram means 3000 kilogram of fuel per second. So for 1 second, it burns 3000 kilograms of fuel and expelling the hot gas thus produced. So when fuel is burned, a hot gas is created. Sometimes normally it is known as smoke. The hot gas is pushed backward. So when we push something to one direction, it gives reaction force, which is known as Newton's third law of motion. Every action has equal and opposite reaction force. So once the burned gas is pushed downward by the rocket's engine, the gas should give upward force to the rocket, and rocket is moved because of that force. The force upward thrust is given by the product of the rate at which the fuel is burned. See, there is a very important word here. There's a very important word, rate. Rate at which the fuel is burned. Rate means something per second. How much fuel is burned per second, which is known as rate. Rate, capital M, at which the fuel is burned, and the exhaust velocity of the gas relative to the shuttle. There is another word, relative. It will be needed later here, velocity. Right. Problem number 1, show that the product mu has dimensions of force. Show that the product mu has the dimensions of force. First of all, tell me what a dimension is there. We have learned that dimension is, right? Dimension is a symbol. Dimension is a symbol, right? So if it is asked us to find the dimensions of force, we should prove that this product mu has the dimensions of force. It means first of all, we should find the dimensions of force there, right? So we know that dimension is some kind of a symbol which represents a physical quantity, right? Dimension is some kind of a symbol. It represents a physical quantity. For example, if I write length, right? If I write length inside square brackets, if I write length inside square bracket, sorry, the meaning is the dimension of length. Dimension of length is capital L. So it's a letter, English letter, right? It's an English letter, right? So if I write mass inside square brackets, the meaning is the dimension of mass. The dimension of mass is capital M. Capital M is a letter, it's a symbol. This symbol M represents the physical quantity mass. The square brackets used to say dimensions of. Similarly, if I write time, if I write time inside square bracket, the meaning is, right? Its meaning is the dimensions of time. The dimensions of time is capital T. The simplest example that we have learned is the first physical quantity that we have learned is velocity. So dimension of velocity, right, is equal to, what is the equation of velocity here? Velocity is displacement divided by, Lamai? Displacement divided
Time taken, sir.
Very good, very good. Displacement divided by time taken. Displacement is a length, some kind of a length. Displacement is the shortest distance between any 2 points. So distance is a length. Therefore, displacement should also be a length. So displacement should have the dimension of length. Time divided by time. So dimension of displacement is equal to the dimension of length. So that is capital L. That is capital L. Dimension of time, capital T. This term T comes up with a minus sign. This term T comes up with a minus sign. Then we get the dimension of velocity as LT to power minus 1. Without saying LT to power minus 1, if you want, we can say LT minus 1. Simply, you can say LT minus 1 if you want. Got it? So the next thing that we have learned under this dimensions lesson, I'm just revising the knowledge. I'm just recalling your memory before I discuss this lesson. The next thing that we have learned is acceleration. Acceleration. So simply, acceleration is increase in velocity divided by time taken. Acceleration is equal to increase in velocity divided by time taken. So I'm not going to write increase in velocity. I'll simply write velocity. So acceleration is, in simple words, velocity divided by time taken, simply. Right? So dimensions of velocity we have already found. We have already found the dimensions of velocity, and we know dimension of time as capital T. Right? So then acceleration equals velocity divided by time taken. Dimensions of velocity is LT minus 1. Time taken is capital T. Time taken is capital T. This term, this T term comes up with the minus sign. It comes up with the minus sign. So LT minus 1. The denominator also comes up with another minus 1. So what will be the final answer here? Finally, LT minus 1 into LT minus 1 into T minus 1. T minus 1 into T minus 1 is T minus, Lamai? T minus
2, sir.
Yes, very good. T minus 2. So LT minus 2 is the dimensions of acceleration. So we have already learned these things. I just recall your memory. Now the thing that we want is the force. So I want some space. What can I do? I'll do something like this. I'll increase this screen further. Like this, right? Then I can find the dimensions of force, right? Dimensions of force. So we know that force equals F equals ma. So dimensions of force should be equal to dimension of m. M means mass into dimensions of acceleration. F equals ma. F equals MA. This is the thing that we want in the examination, right? So dimension of M, dimension of mass, that is capital M. Dimension of mass is capital M. Dimension of acceleration we have already found. What is dimensions of acceleration, dear Lamai?
LT minus 2, sir.
LT minus 2. So M into LT minus 2 means MLT minus 2. MLT minus 2. So the things that you should write depends on your knowledge, right? So if you are 100% okay with the units and dimension lesson, you just want to write only the things I have written with white color. But if you think if you think that it's better for you to have a complete note about some kind of a note for you to recall your memory about dimensions, then write down everything that I have written. It depends on you. Do not ask from me, right? If you think that you want some kind of a note to recall your memory, then write down everything. If you think, okay, I don't want any further descriptions, I remember this lesson, then write only the things that I have written in white color. It's up to you. Quickly write them, write the things that you want. Right now, the most important term here is the rate. See, the force upward thrust is given by the product of the rate capital M at which fuel is burned. So capital M means rate of burning fuel. Am I right here? The rate at which the fuel is burned. So if I write like this, if I write dimensions of capital M, actually it is the dimensions of the rate. It is the dimensions of the rate at which the fuel is burned. At which the fuel is burned. So this is the point you should remember. Right? So rate means something done per second. I think you remember it. Rate means something doing per second, something happening per second. So rate of burning fuel means, right, the amount of fuel burned per second. The amount of fuel burned per second means if I want to find the amount of fuel burned for 1 second, I should do something like this. Amount of the fuel, amount of the burnt fuel, amount of the burnt fuel divided by time taken. Am I right here? The rate at which the fuel is burned mean amount of the fuel burned per second. So amount of the fuel burned per second mean amount of the burned fuel divided by time taken, right? For example, if the amount of fuel burned for simple t seconds, amount of the fuel burned for simple t seconds, let's say simple m. Simple m kilogram is the amount of fuel burned for 1 second, burned for t seconds. Then the amount of fuel burned for 1 second is simple m divided by simple t. Got it? If simple m kilogram is the amount of the fuel burned for simple t seconds, then the amount of the fuel burned for 1 second is m over t. It means amount of the burned fuel divided by time taken. Now we have the required dimensions. Amount of the fuel burned, it is amount mean actually mass. Actually mass of the burned fuel. So mass of the burned fuel mean mass. Dimension of mass is capital M. Time taken, dimension of time taken is capital T. This T comes up with the minus sign, then we get dimensions of capital M mass mt to power minus 1, or simply we say mt minus 1. Mt to power minus 1. But when you write, please write it as a power. So this is the next thing that you should find before you go to prove this one, right? So in the examination, you should write only the things that I have written in white color. You should write only the things that I have written in white color, because other things I have written just to recall your memory as a supporting thing. I just wanted to give you a support. That's why I have written the other things. But in the examination, it is enough if you write the things that I have written in white color. Complete this note, dear. Still, we did not reach to the answer. So we should prove that. Still, we did not reach to the answer. We should prove that the product mu has the dimensions of force. We have found the dimensions of force as mlt minus 2, and we have found the dimensions of capital M, the rate at which the fuel is burned, as mt minus 1. So we want to do one more thing. We are behind one more step, the answer. Is video clear here?
Yes, sir.
Sorry, dear.
Clear, sir.
Right. Do you see any black screen?
No, sir.
Right.
No, sir.
So if video is not clear, if you see any black green screen, just the best thing is leave the class and rejoin. That will work properly. Or select the proper screen. Right. So you may be looking at another different screen. So select the screen at which the video is delivered to you, or just leave the and rejoin. That will work properly. Right. I want some space, so I have to erase the things that I have written in black color. I want space for the final answer. So I have to erase the things that I have written in black color. So if you want, please take a screenshot quick. Right, I'll erase them. Right, I should prove that the product mu has the dimensions of force. So I just want one more step, right? So I'll write the dimensions of capital M into U, mu product is equal to dimension of M into dimension of U. Got it? Right. So then a student asks, why are we taking mass as the rate of burning fuel? Because it's given in the question. Because it's given in the question. You see this sentence? Rate, the product of rate capital M at which the fuel is burned. This is given, you see. It's given here in the question. Product of the rate M at which the fuel is burned. Rate M at which the fuel is burned. If you look at from here, you will identify it. Right. Is it clear here? Is it okay or not? Just send me a message here. You have asked me a question, that's right. If you have any further questions, you can send me a message to Zoom chat so I can help you, right? So now, dimension of capital M. Capital M is the rate at which the fuel is burned. We have found it. We have found it. Dimension of capital M we found as mt to power minus 1. I just write mt minus 1 into U. Dimension of U, whether it is something to relative or not, velocity is a velocity. So dimension of velocity is LT minus 1. LT to power minus 1. Now we have the few things there. You see, capital M is there. Nothing will happen to it, and L will be there. Nothing will happen to L because we have only one L term. How many T terms there? T to power minus 1 into T to power minus 1. What's it here?
T to power minus 2, sir.
Very good. It is T to power minus 2. So what is ML T to power minus 2, dear Lamai?
Dimension of force, sir.
That is the dimensions of force. So this is the answer. In the examination, it is enough to write the things that are written in white color. They will give you the full marks, right? Even you write only this part, even you write dimensions of mu like this, they will give you full marks. So, but I have written a few other things for you to understand the question. Completed there? We cannot use any other equation to prove this because this is a given equation. In the question, it is clearly given. You see that we cannot use our own equation to prove anything because in this question, it is clearly given. It is clearly given that, right? The force means upthrust. The force thrust is given by the product of the rate capital M at which the fuel is burned and the exhaust velocity of the gas relative shuttle. So as they have given the equation, we have to use their equation. And please don't be confused with this thrust. And please don't be confused with this thrust and the thrust that you have learned in Archimedes principle. They also you have learned some kind of an upthrust. So that upthrust and this upthrust are two different things. The upthrust explained in Archimedes principle is given by a liquid. This thrust is given by a hot gas, a smoke, which is generated by burning of fuel. So they are two different things, even the same term is used. Got it, dear? And here it is said upward thrust, upward thrust. Okay, so don't be confused. Shall we go to the next question, dear? Who wants more time to write the things? Lamai? Shall we go to the next question? And the other thing is, if you have not learned this theory, earlier, you have to join to our new class to cover the theory that you have missed, right? We have already covered all these things, right? There may be some students, even we have completed those things in physical classes. There may be some students who were joined, who were in the physical classes when I was discussing this question. So this may be their second time of the discussion for them. But if you have missed, the best thing is joining to the new class, right? So I think the time is enough. Let's go to the next question. Right? So, but if you think that you want more time to write, just take a screenshot. I'll erase. Right, I'll go to the next question. What is the initial acceleration of the thrust of the shuttle as it begins to leave the launching pad? So normally a rocket is placed on a certain horizontal surface, which is made by a very strong material, and it is very it is a very tough material. It is okay for a very high temperatures. Even under high temperatures and forces, that material, right? It is not a simple concrete. That material is withstand for high temperatures and high forces. So a shuttle is placed on such a horizontal surface that is known as launching pad. So once the rocket leaves the launching pad, what will be its acceleration? That's what they have asked. So in this question, they simply said that the upward thrust, see, the upward thrust needed to move the shuttle is 3 into 10 to the power 7 Newton, which is achieved by burning fuel. So it means, what is the force acting on the shuttle there? They have given the force acting on the shuttle indirectly. See, the force acting on the shuttle by burning fuel, they have given it as 3 into 10 to the power 7 Newton. If you read the question, you will find this. The force, the upward thrust given by the engine by burning the fuel is 3 into 10 to the power 7 Newton. But in addition to this force, there should be another force acting on the rocket. Can you guess what that force is there?
mg force, sir.
Yes, very good. There must be the weight of the rocket should be acting vertically downward. Got it? So if we consider a rocket, yes, it has its engine gives a certain force. In addition to that force, there should be the gravitation attraction force. So if I draw a simple figure of a rocket, the weight is acting downward, which is given by the gravity of the earth. In addition to this weight, right? In addition to this weight, there is the force given by the engine of the rocket. So I would like if you draw a simple figure like this to indicate the two forces. The force given by the engine, let me mark it as FENG. It is given in the description as 3 into 10 to the power 7 Newton. So this is the force given by the engine of the rocket, and the weight force mg. So I'm not going to calculate it here. I just leave it as mg Newton. Right, now somebody unmute the mic and tell me the mass of the rocket. It is given in the question. If you read the question carefully, you can find it.
2 into 10 to the power 6 kilograms, sir.
Very good. It is given here. Very good. So the mass of the rocket is given as 2 into 10 to the power 6 kilograms. So I would like if you draw a simple figure and mark these data. Mass of the rocket is given as 2 into 10 to the power 7 Newton. Right. So please use draw a simple figure and mark these data. Mass of the rocket, yes. That's a small mistake. Mass of the rocket is 10 to the power 6 Newton. Yeah, thank you, Buddha. Mass of the rocket is 2 into 10 to the power 6 Newton. Yes, that was a mistake. Please correct it. Sorry.
Sir, kilograms, sir.
Yes, unit is kilogram. Why? Sorry. Yes, unit is kilogram. Correct. So what should I do to find the acceleration, dear? Hello, what should I do to find acceleration, Lamai? Yes.
Sir, apply F is equal to me.
F equals MA equation. What's the direction, the upward or downward?
Upward.
Upward. We should apply F equals MA equation vertically upward. So if you consider this, the upward force acting on the rocket is the force given by the engine, FE. The weight of the rocket acting downward equals mass of the rocket. It's given and acceleration is A. So here we should apply F equals MA equation. So force given by the engine of the rocket is 3 into 10 to the power 7 minus mass of the rocket is 2 into 10 to the power 6 into simple g. I'll write it separately. Value of simple g is 10 equals again mass of the rocket. What's the mass of the rocket, dear? 2 into
10 to the power 6.
Very good. 2 into 10 to the power 6 into acceleration is simple A. So I would like to give a small tip, a small thing which can be used to solve this problem very easily. Listen here, this 3 into 10 to the power 7, this 3 into 10 to the power 7, let me write it as 30 into 10 to the power. Can somebody tell me this value there? 3 into 10 to the power 7, I'm going to write 30 into 10 to the power something. So what should be the power of 10?
10 to the power 6, sir.
10 to the power, I didn't hear.
10 to the power 6, sir.
Very good. 10 to the power 6 minus here. I'm going to do something like this. This 10 and this 2 I'm going to multiply. What is this 2 into 10, dear?
20, sir.
20. So that is 20 into 10 to the power 6. I didn't do anything to that 10 to the power 6 equals here 2 into 10 to the power 6 into simple a. Now, can somebody tell me the reason for me to write this or to keep this 10 to the power 7 to convert into 10 to the power 6? Can somebody tell me the reason behind?
So we can cancel out all the powers.
All the
10 to the power 6 powers are cancelled out.
very good, excellent, Buddha. We can cancel out all the 10 to the power 6 components, right? So once all the 10 to the power 6 components are cancelled out, what will be the remaining terms, dear? This 10 to the power 6, this 10 to the power 6, and this 10 to the power 6 cancelled out. So what will be the remaining terms, dear? 30 minus 20 equals this side only 2a. Am I right? So what is 30 minus 20, dear? Should learn
10,
these
sir.
simple methods of simple.
10.
30 minus 20?
10, sir.
10 equals 2a. 10 equals 2a. So if you take 2 to this side, it will be 10 divided by 2. 10 divided by 2 is 10 divided by 2 is 5. So acceleration can be found as 5. 10 divided by 2. So acceleration equals 10 divided by 2, that is 5 meter per square seconds. 5 meter per square seconds. Got it here? Right. So is there anybody who got this answer earlier before I explain the things here? Anybody? Okay, now your turn. You can write them all. Please write them all quick. Can you see all the things that I have written there? Have I missed anything?
No, sir.
Everything can be seen. Can you see even 5 ms minus 2?
Yes, sir.
Okay, dear. Right. Complete the answer, dear. After that, let's go to the next question. Please tell me once you have written the things. If you have written all the things, send me a message to my Zoom chat saying done. So I'll go to the next part of the question. If you have written all things, send a message to the Zoom chat saying done. what should we think about the burning fuel here? It is everything happens inside the rocket. Everything happens inside the rocket, and the professor has given the force created by burning fuel and its engine and throwing the hot gas through the nozzle is 3 into 10 to the power 7. So it's given there, so we can directly use that thing. It is directly given in the question that after everything, the force generated, the force acted on the engine, acting on the rocket is 10 to the power 3 to 10 to the power 7. So as this is given, we should not worry about the process happening inside the rocket engine and how the fuel burned and that kind of things, because this is directly given. And there's nothing such big process happening inside a rocket engine. The thing is just fuel is burned. So after that, there is no space for the hot gas to stay in the rocket. Therefore, hot gas is pushed outside by the nozzle. So when gas is pushing outside, the gas should give equal and opposite force to the rocket according to Newton's third law. So it will be moved. Right. I think I have answered your question, but if you have further doubts, you can send a message to Zoom chat. Right. So let's go to the next question. So I want to erase all the things that I have written and drawn on the figure. So if you want any more time to write the things, please take a screenshot. I'm going to go to the next question. So whenever I say that I'm going to go to the next question, please take a screenshot if you want any more time. So I'll erase them. Right, so let's go to the next question. Right, so what is the next question there? Roman number 1 completed, Roman number 2 completed, Roman number 3. Assuming that the acceleration of the shuttle is constant, assuming that the acceleration of the shuttle is constant, determine the velocity of the shuttle after 30 seconds. So actually, that's a very simple part there. It's so simple, right? So if the acceleration is constant, if the rocket is, they ask us to assume. Actually, the correct thing is the real situation is a rocket is not moved with the constant acceleration. But here, professor tells us it's moving with the constant acceleration. So if he tells us, and we just assume it for a period of 30 seconds, so it means professor's assumption is correct. You see. For a 30 seconds is a very small time period. For a very small time period, the force may be constant, acceleration may be constant, yes. Right. Then to find the velocity after 30 seconds, right? The rocket starts to move at rest. It has an acceleration of 5 meters per square seconds. It is moving vertically upward. So what's the equation that should I apply to find the velocity after 30 seconds? Lamai?
So V equals U plus AT.
Very good. We should apply V equals U plus AT. We must indicate the direction, right? Because we are dealing with vectors. For each and every vector, we must indicate the direction. So initial velocity of the rocket is 0. Acceleration of the rocket. Rocket is not a stone. Sometimes the students ask, why don't we take acceleration of the rocket as 10 meters per second, gravitation acceleration? Rocket is not moved freely under the gravity. Think about the word freely. A rocket has its own engine. So the engine produces an external force on the rocket. As the engine gives an external force to the rocket, a rocket has its own acceleration. As the engine of the rocket produces an external force, a rocket has its own acceleration. Therefore, acceleration is not 10, it is 5. So acceleration is 5. Time taken for the motion is 30. So nothing will happen to this. 0. 5 times 30 is 150. So what is the velocity of the rocket after 30 seconds, dear? Lamai, what is the acceleration of the rocket after 30 seconds?
150 meters per second, sir.
150 meter per second, right? Complete it, dear. Right, what do you think about Roman number 4? Calculate the exhaust velocity of the gas relative to the shuttle. Right. What is the force acting on the rocket, dear? Somebody please tell me. Roman number 4 asks, calculate the exhaust velocity of the gas relative to the shuttle. So what is the force acting on the shuttle? Do you remember it? See, if we go backward, you see the force acting on the rocket is given. So what is it? 3 into 10 to the power 7. So what is the force acting on the rocket, dear? Lamai?
3 into 10 to the power 7 Newton.
3 into 10 to the power 7. How that force is obtained, dear? That force is obtained by burning 3000 kilogram, 3 into 10 to the power 3 kilogram of fuel per second. And the other thing that they have given is this equation. What is this equation here? The upward thrust is given by the product of the rate capital M at which the fuel is burned and the velocity, exhaust velocity of the burned gas relative to the shuttle. So they have given us the force. They have given the mass of fuel burned per second, right? You see, per second. So mass of fuel burned per second means rate of burning fuel, the rate at which the fuel is burnt. They have given the value of M. This is capital M. They have given the force. They have asked us to find the velocity of the exhaust gas relative to the shuttle. That's what they have asked. Can you see it there? What are the things that they have given? They have given us the equation. What is the equation that we should use there? What's the equation that we should use? Thrust or the force acting on the rocket is equal to the product capital M into U, simple U. Capital M is the rate at which the fuel is burned. It is given. It is given. And the thrust is the force generated by the burning fuel, that is given as 3 into 10 to the power 3 into 10 to the power 7. It's given. Mass of the fuel burned per second, the rate at which the fuel is burned, is given as 3 into 10 to the power 3 into 10 to the power 3. So the only thing that we want to find is U. U is the velocity of the exhaust gas relative to the shuttle. So please use this equation and try to calculate the value of U. Start there. Give a try to find the value of U quick. So this is the answer for Roman number 3. This is the answer for Roman number 3. No, not Roman number 3. Roman number 4. This is the answer for Roman number 4. Start. So actually, it's so simple because everything is given in the question. They have said of a certain 3,000 kilogram of fuel is burned in the rocket, and that fuel is pushed out through a certain nozzle. Because of that pushing, a force is generated on the rocket. A force is generated on the rocket, and that force is given as 3 into 10 to the power. That force is given as 3 into 10 to the power 7 Newton. So all the things are given. All the things are given. So it's very easy to do the calculation, find the V. Not V, U. Right? So it's not such a big thing because all the things are given, right? As all the things are given, we just want to put the numerical values and do the calculations. That's it. Right. So I think you should keep your eyes open here. Can somebody unmute the mic and read? Wait, I'll show you a sentence. Can somebody read this? Can somebody read the things that are written inside this square, this box there? Please.
Velocity U of the gas relative.
I'll add this also. Now read the things inside the two yellow color boxes.
Velocity U of the gas relative to the shuttle.
So what is U then?
Velocity.
U is the velocity of the gas relative to the shuttle. We are calculating it, right? Okay, thank you, dear. Right, U is the velocity of the gas relative to the shuttle. So let's do the calculations. Right. So what are things that can be cancelled out here? This 3 and this 3 will be cancelled out. 10 to the power 3 can be taken to this side by cross multiplication. 3 and 3 will be cancelled out. Even if you do not calculate, cut it, no problem. So 3 into 10 to the power 7. Multiplication 3 into 10 to the power 3 come to this side as division. So 3 into 10 to the power 3 will come to the denominator side. Once we use cross multiplication, then the remaining term, the only remaining term at the right hand side will be U. U will be the remaining terms. 3 into 10 to the power 3 is taken to this side. Now you see that this 3 and this 3 cancelled out. Then what will be the value of U here? U equals 10 to the power 7 is there. 10 to the power 7 is there. So this denominator, the denominator 10 to the power 3, the denominator 10 to the power 3, this one, the denominator 10 to the power 3 comes up as 10 to the power minus 3. So what is the final answer then? U equals, Lamai?
10 to the power 4.
10 to the power 4.
Very good, very good, excellent. 10 to the power plus 7, 10 to the power minus 3. So 7 minus 3 is 4. So that is 10 to the power plus 4 meter per second. So what is 10 to the power 4 means? How many? Can you give it in simple terms, dear? What is it, dear?
10,000, sir.
10,000 meters per second. Very good. 10,000 meters per second. So what is the velocity of the exhaust gas relative to the shuttle, dear?
10,000 meters per second.
10,000 meters per second. That's the answer. Complete it, dear. Write it. All the things are given in the paragraph. If you read the description, actually even we cannot consider this, still we cannot consider this question as an advanced level question. If you know this units, this dimension section, there's nothing. All the other things are given. We just want to put the equations. We just want to put the numbers that they are given, that they have given to the equation that they have given. They have given the equation. They have given the numbers. We just want to put the numbers and do the calculation. So it is actually it's some kind of a O-level maths question. So simple. Complete it here. Right, so we have found the answers for Roman number 3 and Roman number 4. So we should go to Roman number 5. Right, so I will not erase the things. I just move the screen up to see to check the things asked in Roman number 5. I'll move it further up. As I remember, there was a small typing mistake because Roman number 4 and 6, 5 and 6 should be the same question. It should not be broken into 2 sections. It should be the same thing as I remember. There was a typing mistake. I don't remember. What is calculate the exhaust velocity relative to the shuttle? What is the exhaust velocity of the gas relative to the earth? So what are the two differences here? Can you see small differences in Roman number 4 and 5? In Roman number 4, they ask velocity of the gas relative to the shuttle. Can you see? In Roman number 5, they ask velocity of the same gas, velocity of the same exhaust gas relative to the earth. Got it? Can you see the two differences there? Roman number 4, what is the velocity of the exhaust gas? Actually, the smoke coming out from the rocket. Velocity of the exhaust gas relative to the shuttle. That's what we have found as 10,000. The next thing that they have asked, the velocity of the gas relative to the earth. So what's the equation that we use to find the relative velocity here? If you want, you can use VA, B equation, but I don't recommend it. I have given you a very simple equation than that to find a relative velocity. What is it here? Lamai? To find the relative velocity, I have given you a very simple equation than VA, B. What is it?
S over T, sir.
Yes, dear.
S over T.
Listen, I'll recall your memory. The rocket is moving up, right? The rocket is moving up. Let me take it as V1. After 30 seconds, velocity of the rocket is V1. We have found it as 150 meters per second. Where did we find it here? Here. Sometimes you may have forgotten. So this is the place where we found the velocity of the rocket after 30 seconds. That's why I didn't erase it. That's I kept it for you. I know that you definitely forget it. So what is 150 meters per second? It is the velocity of the rocket after 30 seconds. So I have marked it as V1, right? Then the next thing is the velocity of the exhaust gas relative to the rocket. So listen there. If I consider the rocket, right? Let me use a different color for the rocket. So if this is the rocket, what is the velocity of the rocket, dear? Lamai?
150 meters per second.
150 meters per second, right? Then, right, so this is the velocity of the rocket after 30 seconds. What is the velocity of the exhaust gas relative to the rocket? That is the case, right? So what is this 10,000 actually? What is that 10,000? 10,000 is the velocity of the smoke relative to the rocket. So it should be written like this. Velocity of the gas, exhaust gas actually, relative to the rocket or the shuttle. Let's use the word that they have given. We have found this as 10,000 meters per second. Right. So if you are not learn relative motion, it's not my problem, right? You may be late to join to my class, so it's not my problem, right? So the only thing that I can do is I have arranged a new class for the new students. So you have to join to that class and cover the things that you have missed. So as a help for you, right? But the student who were with me from the very beginning of the class, they should know all these things, right? Now you see there, let's say somebody is looking at this rocket. Somebody is looking at this rocket. Somebody is on the earth. There is a person. That's how we imagine the things. There is a person, he is at rest on the earth. And that person is looking at the rocket. According to that person, the velocity of the exhaust gas relative to a stationary man on the earth is said to be the velocity of the gas relative to the earth. Can you remember that point there? What's the
Yes,
what is
sir.
the yes, dear? I didn't hear you, Buddha.
I said yes, sir.
Right. So let's say this is the earth. This is the earth. Right. A man on the earth, listen carefully, a man on the earth, just exactly, let's say he is just below the rocket. He is looking at the rocket. Is this man moving there, Lamai?
No, sir.
No, he is not
No,
moving.
sir.
He is at rest on the earth. I'm just explaining because sometimes you may have forgotten this theory. There is a man, he is at rest on the earth. So he is looking at this rocket. So what is the velocity of the rocket as as observed by this person there? I
Sir,
think you know the
150
law
meters
of my
per second.
class. You must talk to me. You must answer my question. So as observed by this man, what is the velocity of the rocket?
Sir, 150 meters per second.
150 meter per second. That's why we call the velocity of the rocket relative to the earth is 150 meter, right? So velocity of something as observed by a stationary man on the earth is said to be the velocity relative to the earth. So velocity relative to the earth of the rocket is V1, it is 150 meter per second. But velocity of the gas is given relative to the shuttle. What's the meaning of relative to the shuttle here? Can you tell me?
So maybe the velocity of the gas when we consider the shuttle as it is stationary.
Okay, I'll give you a help. I'll give you a help. You see, this science means physics is not a subject like this, dear. Unfortunately, I have seen some questions like this. Listen to me, this story, dear. I have seen some questions like this in your mechanics tubes, some of mechanics tubes, not my tubes, right? What is velocity? What is displacement? What is distance? What is the difference between distance and displacement? Explain the difference between speed and velocity. Do you think that kind of question will be asked in advanced level physics paper? So this is not O-level science, Appa. This is not O-level science, especially this is not advanced, this is not biology. This is physics. In physics, they will never ask you to write that kind of things. What is the difference between speed and velocity? write down and description about velocity for 10 lines. Do you think that kind of things asked in advanced level physics? This is university entrance examination. What is this, dear? What is advanced level meaning? Is it O-level part 2? Lamai?
No, sir.
No, sir.
No, sir.
Velocity කියන්නේ මොකද්ද? high speed කියන්නේ මොකද්ද කියන්නකෝ එහෙනම්. ඒ දෙකේ වෙනස කියන්නකෝ මොකද්ද කියලා අප්පා. ඔය වගේ ගොබ්බ ප්‍රශ්න අහනවාද ඒ ලෙවල් වල? මන් දන්නේ ඇයි කියලා. Please don't think this is not a grade 5 scholarship examination. This is a very tough examination and it's very, very competitive. It's highly competitive. That's why you are paying us, dear. Right? Right. Now let's come back to the story. You want to develop this kind of things. Right. I'm asking something something came to Einstein's mind, right? This is something came to Einstein's mind, not something came to a grade 5 scholarship student, right? Right. So this velocity of the gas relative to the shuttle, this is what we want to explain, right? Now I have indicated a special person. What is the special person? I have indicated a special person on the earth. This one, who is he? He is a stationary man on the earth. According to this man, as this man observed, according to this man, if somebody asks what is the velocity of the rocket, if somebody asks what is the velocity of the rocket as you observe, he will say 150 meters per second. Meaning is distance between this man and the rocket increases by 150 meters, 150 meters by each and every second. Got it? What's the meaning of this 150 meters per second? Very interesting things there. Do not try to memorize. This is not a memorizing a poem and rewriting a poem. That is literature. This is science. Right, listen dear. Listen very carefully. Right? I'm just not explaining. I'm not just giving the answers for past paper questions. Listen. So let's say the gap between the time at which we consider the gap between man and the shuttle. Listen very carefully. I know that very good talented students are here, right? The initial gap between them, the time period at which we consider, let's say initial gap between them, let's say 1000 meters, for example, 1000 meters, right? Now my question is, what will be the distance between them, the man and the rocket, after 1 second? Can somebody tell me? I'll ask the question again. Listen carefully. The initial gap between them, between this man and the bottom of the rocket, is 1000 meters. Velocity of the rocket is 150 meters per second relative to this stationary man. So my question is, what will be the gap between them, distance between rocket and the man after 1 second? Somebody unmute the mic and tell me.
1150 meters.
1150. Very good.
50 meters.
So that is the meaning there. That's the practical meaning of velocity. The velocity of the rocket relative to the man is 150 meters per second, means after each and every second, the gap between them increases by 150 meters. So after 1 second, 1000 meters will become 1150. So what will be the gap between man and the rocket after 2 seconds?
1300 meters.
1300 meters, because after 1 second gap is increased by 150. Then the gap between the man and the rocket is 1150. After 1 more second, gap will be increased by another 150 meters. So 1150 plus this 150 will be 1300 meters. So that's the meaning there, right? Now my question is, let's come back to the main story. Right? So velocity of the rocket relative to the earth means velocity as observed by a man on the earth. So what is the meaning of this dear? Velocity of the gas relative to the shuttle. What does it mean? Can you give me a simple answer for it?
So calculating the velocity of the gas, considering the shuttle to be at rest.
Shuttle is not at rest. It is moving. It is moving. I explained a lot, right? So let me ask the same question once again. Listen to me carefully. Listen to me carefully. Velocity of the shuttle relative to the earth. Velocity of any object relative to the earth means the velocity of that object as observed by a stationary man on the earth. So my question is, what is the velocity? What's the meaning, practical meaning of the velocity of the gas relative to the shuttle? Somebody give a try.
The velocity of the gas as observed by a person in the shuttle.
Excellent, Buddha. Excellent. I'm so happy to have you in my class. Right. So I am very happy to have you in my class. Even I should pay you. Very good. So velocity of the shuttle relative to the earth mean velocity of the shuttle as observed by a man, a stationary man on the earth. Similarly, if there is a man on this shuttle, what will be the velocity of the exhaust gas as observed by this man, which is known as velocity of the exhaust gas relative to the shuttle? That is the simplest meaning there. May I again explain? Who would like if I explain again? Lamai? Right, listen carefully. Velocity of something relative to the earth means velocity of that object as observed by a stationary man on the earth. So similarly, velocity of the gas relative to the shuttle means if there is a man in this shuttle, if there's a man inside this shuttle, as observed by him, what will be the velocity of the gas? That is 10,000 meters per second. So according to a man inside this shuttle, the velocity of the exhaust gas is 10,000 meters per second. That is said to be the velocity of the gas relative to the shuttle. It has another meaning. This 10,000 meters per second has another meaning. May I explain that meaning also? Please give me the permission. Raise your hands up if you would like to listen to that meaning also. Lamai, give me the permission, quick. Not enough votes. Not enough. Give me more words to explain that. Okay, good. I got 2 out of 3 powers. Good. Now listen there. The velocity of the gas relative to the shuttle is 10,000 meters per second means the distance between this hot gas, let me use a color and draw it. The distance between this gas, burnt gas. Let's say this is the burnt gas, right? I indicate like this. So this is the hot burnt gas, right? So this gap between this burnt gas and the rocket increases by 10,000 meters within each and every second. If the initial distance between the rocket and the gas is 0, because it's already inside the rocket. If the initial distance between the rocket and the gas is 0 meters, the distance between rocket and gas will be 10,000 meters after 1 second. After 2 seconds, the gap between rocket and the burnt gas will be 20,000 meters. So what will be the gap between the burnt gas and the rocket after 3 seconds? Somebody unmute the mic and tell me, dear.
30,000 meters.
30,000 meters per second.
Can you understand the meaning of this here? So this man, the man inside the rocket will tell you that the gap between me and the burnt gas increases by 10,000 meters for each and every second. Got it, dear? Clear or not?
Clear, sir.
That is
Clear,
the
sir.
meaning of this 10,000. That is the meaning of this 10,000. Got it? Right. Now we are going to find, I just explained those things. They have asked us, what is the velocity of the exhaust gas relative to the earth? relative to the earth. So now you see this gas, this gas and the rocket are moving away from each other. So actually it is, let me move it a little bit away. Let me erase it. Right. So what is V1, dear? Lamai, what is V1? Here, look at V1 and tell me what is V1?
150 meters per second.
150 meter per second. What is V1? Velocity of the rocket relative to the earth. What is V1, dear? Velocity of the rocket relative to the earth. Right. Now, if I mark velocity of the gas relative to the earth as V2, the question asks us to find the value of V2. So what is V2, dear? What is V2? V2 is the velocity of the gas, exhaust gas, relative to the earth. Relative to the earth. Right. My question is, how do we find if two things are moving along the same straight line into the opposite directions? How do we find their relative velocity here? We have learned it. Somebody unmute the mic and
summation of the velocities.
Very good, excellent. If two things, what are two things here? The rocket and the burnt gas. So the rocket and the burnt gas are moving away from each other along the same straight line into the opposite directions. So the relative velocity means the velocity. Relative velocity means the summation of the two velocities. Do you remember it here? Okay or not?
Okay, sir.
Right. So
Yes, sir.
always remember this point here. Velocity of something relative to the earth mean, the simplest meaning is if there is a stationary man on the earth, as he observe what the velocity of the object, what will be the velocity of the object? That is the velocity of the object relative to the earth. Similarly, if there's a man inside a rocket, according to as that person, as the person inside the rocket, as he observes, the velocity of the gas will be the velocity of the gas relative to the shuttle. Right? If you want any further explanation, you can ask me. I would like if you draw this diagram. I would like if you draw this diagram. That will be a big help for you to understand these questions once you read this question later at home. Yeah, you must have a good note. You must have explanation. See, I have the ability to just give you the answer and leave the question there. Am I right? Listen there. I can simply say our relative velocity. It's so simple. Just add V1 and V2. That is the relative velocity. I had the ability to skip the question within 10 seconds. Did I do something like that? Did I do it? Just tell me yes or no.
No, sir.
No, sir.
No, I didn't. I explained a lot, answering all the questions asked by all the students. Why is that? Why is that there? You don't know the reason actually. You don't know the reason for me to explain the things like this much, because this is the real level of examination. This is 2003 question, but you are going to sit for the examination maybe after 20 years of 2003. So things will be much more harder than 2003, right? So therefore, I must explain all the each and every corners of this question. All the facts should be given. Then only you are prepared for the examination. Otherwise, if you want to know if you want to know only the answers, just get a photocopy of the marking scheme, dear. Just get a photocopy of the marking scheme. Then you have the answers. Then why do you hire a teacher by paying a fee? No need me. So teacher is not a person who is giving printed marking scheme. The teacher is a person who's able to explain the things properly in simple words. Especially in physics, teachers should be able to think in simple words, and everybody should be able to understand once a teacher explains the things. Who said it there? That's not my idea.
Albert Einstein.
Albert Einstein. How did he say it here? I would like to explain it. How did he tell it? I'm asking Einstein's word there. I think you know it.
If you can't explain anything to anyone without
If
seeing
you
the book,
can't
you are not understood.
Very
If
good,
you
very
can't
good.
explain
Yes,
it
dear.
simply,
Oshati?
you can't understand. If you can't explain it simply, you can't understand.
Very good, dear. Because sometimes, actually, both of you have told me the same thing. Unfortunately, he said it in German language because his mother tongue was German, not English. Therefore, we are just giving his translations. He said, if you can't explain something simply, you don't understand it well enough. You don't understand it well enough if you can't explain something simply. So if you want to be someone, if you would like to build a good knowledge on physics, build the ability of explaining things. That's what I am doing here, dear. Right. Okay. So just put a star point and write. I think you have drawn the figure. Is there anybody who wants more time to draw the figure? Lamai?
Done, sir.
Done, sir.
Okay, let's go. Velocity. Sorry, please write. The rocket and the exhaust gas. The rocket and the exhaust gas are moving along the same path into the opposite directions. The rocket and the, even it is shuttle, I don't care whether it is shuttle or a rocket, same, not same, but it's okay. The rocket and the exhaust gas moving along the same path into the opposite directions. Therefore, the relative velocity is the summation of the two velocities. Therefore, the relative velocity is the summation of the two velocities. The rocket and the gas moving along the same path into the opposite directions. Therefore, the relative velocity is the summation of the two velocities. The relative velocity is the summation of the two velocities. So let me use that equation. So what is the equation that I use? Velocity of the gas relative to the rocket or the shuttle. The shuttle and the gas are moving along the same path into the opposite directions. So therefore, velocity of the gas relative to the shuttle is the summation of the two velocities, V1 and V2. So please remember that V1 and V2 are two velocities relative to the Earth. V1, V2 velocities relative to the Earth. Got it, dear? Can somebody read that sentence again, dear? The sentence that I have given 1 minute earlier, just before this equation. Somebody please read.
The rocket and the exhaust gas are moving on the same path into the opposite directions. Therefore, the relative velocity is the summation of the two velocities.
Very good. Thank you, dear. The rocket and the gas are moving along the same path, into the opposite directions. Therefore, the relative velocity is the summation of the two velocities. The two velocities mean V1 and V2. V1 and V2 are the velocities relative to the Earth. But we know this one, dear. What is the velocity of the gas relative to the shuttle, dear? We have calculated it. What is it, dear?
10,000.
10,000 meters per
10,000.
second.
Velocity of the exhaust gas relative to the shuttle is 10,000. 10,000. Right? So we have calculated here, you see. Here we have calculated. This place, you see this one, this 10,000 meters. This is the place where we calculated it. Right now, V1 is the velocity of the shuttle relative to the Earth. What is it, dear?
150 meters per second.
150 meters per
Per
second.
second.
Very good, 150 meters per second. So we just want to find V2. Can you do the rest and find V2, dear? Start and send your answers to my Zoom chat. Right, so it's a very simple calculation here. You see this is 10,000. This is 10,000, right? Positive 150 come to this side as minus 150. V2 will be there at the other side. Am I right? It's such a simple, quick calculation. 10,000 minus 150. What is it here? V2 equals 10,000 minus 150. Lamai?
9,800.
9,850. Yes, very good. So it's simple, right? You just want to subtract. Positive something goes to other side as division something. So that's the answer, right? So is the story clear here? Right. And please don't take a high effort to understand this on the spot, because you will find so many questions like this in my tudes and even in past papers, right? The only thing that you want to remember is relative velocity of something means velocity relative to the Earth mean it is the velocity observed by a stationary man on the Earth. Velocity of one object relative to the another object mean the person, a stationary person, should be on the object. For example, velocity of the gas relative to the rocket. Velocity of the gas relative to the rocket mean the velocity of the gas as observed by a man in the rocket. This 10,000 means the 10,000 velocity of the exhaust gas is 10,000 meter per second relative to the shuttle mean the gap between the distance between the gas and the rocket increases by 10,000 meters for each and every second. That's it. Right, Lamai, shall we go to the next question, dear? Give me the permission. Raise your hands up and give me the
Okay, sir.
Okay, sir.
Okay, I'll erase them.
Okay,
I'll erase these things then. I don't want any of these things any further. As I have used them, I don't want them any further. I erase them. That's what we do normally. Once the use is over, we throw them away. Human nature. We have used them, now we don't want them, so we just throw them away. Right, so let's go to the next question. Right. Let me erase these lines because we don't. Oh, what has happened? I didn't want her to erase it. Right. So question number 6. Can you see it here? I think you are able to see the question number 6. Can somebody read Roman number 6? Unmute the mic and read Roman number 6.
A student states that the shuttle cannot accelerate if there is no atmosphere outside. Is this statement correct? Explain your answer.
Okay, thank you. Very interesting question. Even you don't know physics, you can answer this question. I'm very much thankful to the student who read this question. And the other thing is, even if you do not know physics, you can answer this question. How? A student states that the shuttle cannot accelerate if there is no atmosphere outside. Is this statement correct? What do you think, dear? Raise your hands up if you think that student is correct. First word, you give the words to the student. If you think that student is correct, student statement is correct, raise your hands up. Don't wait for the others. Just raise your hands up. Give your vote. So others think student is wrong, right? Actually, I think half. So half of the student think this student is correct. The other half of the students in the class think that student is right. How do you give the answer? I have said that you can give this answer even you don't know any physics. How? You can give the answer even you don't know any physics. Listen dear, have you ever heard that humans have sent a rocket to the moon? Have you ever heard that story, dear Lamai?
Yes, sir.
Right.
Yes, sir.
Is there any atmosphere around the moon? Just tell me yes or no, quick. Is there
No, sir.
an atmosphere
No,
around
sir.
the moon or not?
Yes, sir.
Huh? I didn't hear you properly. Does the
No, sir.
moon have an atmosphere?
No, sir.
No.
No, sir.
It means, let's say when the rocket is launched from the Earth, rocket was able to accelerate by using the Earth's atmosphere. You can think like that. But once the rocket landed on the moon, once the people tried to return to the Earth, there is no atmosphere on around the moon. Then rocket cannot accelerate. Cannot accelerate means there must be a force to accelerate. So without no atmosphere, so rocket cannot accelerate, so it cannot come back to the Earth. So it means Neil Armstrong is still on the moon. Am I right? Is he still on the moon?
No, sir.
No.
Sir.
Neil Armstrong was the first person who landed on the moon. He returned to the Earth. So it means rocket had the ability to accelerate whether there is no atmosphere. Am I right, dear? Am I right or wrong? Just if you think I'm right, just raise your
Yes,
hand.
sir.
The Zoom has given you ability to move your hands up and down. Listen. Once by using the Earth's atmosphere, yeah, rocket is able to accelerate and move to the moon. It is okay to land on the moon. But once in the return journey, the rocket has to accelerate towards the Earth. Then only it is able to come to the Earth. So Neil Armstrong has traveled to the moon and came back to the Earth. And even after that, so many people traveled to the moon and came back to the Earth, right? Yes. So it means the rocket must have an ability to accelerate even without an atmosphere. Am I right, dear? If you think that I am right, just raise your hand up. If I am right, this student is wrong, right? Because he says, he tells us that the shuttle cannot accelerate. So that's why I said, even if you do not know any physics, you can give the answer for this question. So is student correct or wrong, Lamai?
Wrong, sir.
He is wrong because
sir.
rockets are able to travel in space. Most of the space is empty, no particles, a vacuum actually. So therefore student is wrong. You got that answer without knowing any physics. But how do we explain that answer according to the physics that we have learned? How do we explain that story according to the physics that we have learned? So here it is clearly said, even at the beginning of the question, it is said that fuel is burnt, and that burnt fuel is thrown through a nozzle. When burnt fuel is known as exhaust gas, smoke. When that gas is pushed out from the rocket, we have to give a force to the gas. When the gas is pushed downward, right? When the gas is pushed downward by the rocket, a force must be applied on the gas. So if I consider this is this is the rocket, and if I consider this as the burnt gas, right? So to push this gas, I'll just keep a gap between them. I just keep a gap between them, right? To push this gas downward, the rocket must apply a force on it. Am I right, dear? Then only it can be pushed down, right? So the nozzle, or due to the pressure created on it, a force must be applied on this gas. So the rocket has given a downward force on the gas. That's why the gas is moving down. According to Newton's third law of motion, the gas should give equal and opposite force to the rocket. So rocket is moved due to that force. Have I used even the word atmosphere to explain this, dear? Have I used even the word atmosphere to explain this story? Lamai?
No, sir.
No, sir.
No, I didn't use. Therefore, an atmosphere is not needed for this process. Okay or not?
Okay, sir.
Okay, sir.
Right. For the Roman number 6, please write. For the Roman number 6, please write. The fuel is burnt inside the rocket, and the fuel is a fuel is burnt inside the rocket, and a hot gas is created by that process. A fuel is burnt inside the rocket, and a hot gas is created by that process. A hot gas is created by that process. Full stop. That hot gas is pushed away from the rocket. That hot gas is pushed away from the rocket. Away from the rocket. That hot gas is pushed away from the rocket. Full stop. For the gas to be pushed, for the hot gas to be pushed away from the rocket, the hot gas to be pushed away from the rocket, the hot gas to be pushed away from the rocket, comma, a force must be given by the rocket to the gas. A force must be given by the rocket to the hot gas. A force must be given by the rocket to the hot gas. To the hot gas. Full stop. According to Newton's third law of motion, according to Newton's third law of motion, according to Newton's third law of motion, comma, the hot gas must give, according to Newton's third law of motion, the hot gas must give equal and opposite force. The hot gas must give equal and opposite force to the rocket. Equal and opposite force to the rocket. Full stop. The rocket is moved due to that reaction force. The rocket is moved due to that reaction force. The rocket is moved due to that reaction force. Full stop. An atmosphere is not needed for this process. An atmosphere is not needed for this process. An atmosphere is not needed for this process. Therefore, student's statement, student's possessive ways, student's statement is wrong. The student's statement is wrong, or student's statement is incorrect. Therefore, the student's statement is wrong, or you can say incorrect. Okay, dear? Lamai?
Okay, sir.
Right. Somebody please unmute the mic and read that answer. Somebody in the class, please.
A fuel is burnt inside the rocket and a hot gas is created by that process. That hot gas is pushed away from the rocket. For the hot gas to be pushed away from the rocket, a force must be given by the rocket to the hot gas. According to Newton's third law of motion, the hot gas must give equal and opposite force to the rocket. The rocket is moved due to that reaction force. An atmosphere isn't needed for this process. Therefore, student's statement is wrong.
Very good. Thank you very much, dear. So I'm going to erase everything. We should be very much grateful to that student, because there may be some students who are not able to write the answer. So she helped us. We should be very much grateful to her. Do you want any more time to draw these things or write down these things? If you want, please take a screenshot. I am going to erase them all. Did you see some strange word written on my tube, dear? Anybody in the class?
Yes, sir.
What's it? Can you circle it? Or can you read it?
Main come for something.
Have you ever heard it, dear? This term?
Yes, sir.
Anybody?
Yes, sir.
What's it there?
The book written by Hitler.
Yeah, that is the book written by Hitler. Its name of the book was Mein Kampf. Mein Kampf. That book, he explained how to develop Germany and how to make Germany into a very powerful country. But at the time when he was written it, the Germany was very poor. People were dying due to hunger. But Hitler was able to convert the country into a very powerful country, and he was continued the Second World War. It means, I'm not going to talk about Second World War. He converted a very weak country into a very strong country and created a world war, a war against the entire world. So what's the relationship between my physics class and this Mein Kampf here? Can somebody explain? Can somebody guess? Actually, advanced level examination of Sri Lanka is very much tough than a world war. So teaching and making students, converting students to get A for a subject in Sri Lankan advanced level physics is much more tough than a world war. That's why I put it here. Got it? So this is this is a hard, difficult than a world war. So I put this term to symbolize it as a symbol that examination is very tough and we are doing it. You are the soldiers of that world war, right? So I should create a strong students with great personality to face that world war. Yes, dear, your answer is 100% correct. Got it? So this is some kind of a war and it's very difficult. And the other thing, due to a war, what will happen here? Due to the Second World War, what has happened? Millions of people die, am I right?
Yes, sir.
So many people, so many lives were destroyed. Am I right, dear?
Yes, sir.
It was a disaster. It was a disaster. We should not even admire it by even a single word. It was a disaster. Same thing happens due to the advanced level examination of Sri Lanka. For some people, it becomes some kind of gems, jewelries, money, wealth, everything. But many of the people will die. Their body may be survived, but internally they are dead bodies. Humans are wasted due to this tough examination. Therefore, from the very beginning, please be ready for the examination and select good teachers who are able to train you to face this war. Got it, dear? Otherwise, you will fail. If you do not have a good training under a good teacher, you will die in the battlefield. You will not be successful. So that's the story behind this Mein Kampf. So this is the meaning of Mein Kampf is my war. So this is my war with my students, again, advanced level examination. My soldiers are my students. They should be strong enough to face the exam and get A4 physics. Got it, dear? Who understood it? Please raise your hand up if you have understood it. Right, very good. So you know the reality, you know the truth. Once you know the truth, it's even truth may be bitter, but truth is truth. Truth is always better than lies. So now you know the nature. So let's go to the next part of the question, right? Truth may be better, but truth is always very much better than lies. So let's go to the next part of the question. Let me increase the size of the question. Why can't I move it? Let me move it away and let me increase the size of the question. Yeah, this is enough. Right. So let me put my head in again as the paper class is. Right. Whether it is a paper class or a theory class, this is a discussion. A question is discussed. Right. Now somebody unmute the mic and read Roman number 7. Read.
In reality, the acceleration of the shuttle increases as it burns fuel, even though the upward thrust on the shuttle is constant. Explain this statement.
Very good. Thank you very much, dear. In reality, acceleration of the shuttle increases as it burns fuel, even though upward thrust on the shuttle is constant. Upward thrust means upward force. Upward force acting on the shuttle is constant, but they have told that. But they have told us the acceleration increases. How is it possible, dear? They have. Yes, dear.
So the mass of the rocket decreases, so the acceleration increases.
Very good. Acceleration increases because mass of the shuttle decrease. How? How the mass of the shuttle decrease, dear?
Because
So the fuel is
burned.
burned.
Because the fuel is burned. So I think you know this one. The thrust is constant. The thrust means force acting on the rocket is constant. We know that if F is constant, according to F equals ma equation, acceleration should be constant. If F is constant, according to F equals ma equation, the force should be constant, right? Acceleration should be constant. But here, acceleration increases with the time. Why is that here?
So because the fuel is burnt and the mass of the rocket is decreased.
Very good. So huge amount of the mass of the rocket is its fuel. The fuel tank has a larger mass than the entire rocket. You see how many kilograms of fuel is burned per second? It is given in the question at the very beginning. At the beginning of the question, if you read the question carefully, it is said that 3 into 10 to the power 3. Am I right, dear? This much of fuel is burned per second. So it means 3 into 10 to the power 3 kilogram means 3000 kilogram of fuel is burned per second. Therefore, what will be the amount of fuel burned per second, dear? This should be multiplied by 3600. If the rocket travels for a period of 10 hours, so this much of fuel is burned. The rocket has to carry this entire mass. So what will be this total mass, dear? 3 into 10 to the power means 3 means 3000 into 3600. 3000 into 3600 multiplied by 10 hours. Can you understand? So it means the rocket has a huge fuel tank. A huge amount of fuel should be stored in the rocket. So once the fuel is burned, it is converted into a gas and going away, leaves the rocket. Therefore, the mass of the rocket reduces. As the mass is reduced, if the force is constant, according to F equals ma equation, acceleration should be increased. Is it clear, or may I again explain? Lamai? Would like if I explain the story again? Raise your hands up if you would like to. If you would like, if I explain the story again. Good. Very good. Any other students who would like if I explain the story again? Raise your hands up there. Right. I'll explain after I giving you the answer. For the Roman number 7, please write. For the Roman number 7, please write. When the fuel is burned, Roman number 7, when the fuel is burned, it is converted into a hot gas and when the fuel is burned, it is converted into a hot gas and that gas leaves the rocket. When the fuel is burned, it is converted into a hot gas and that gas leaves the rocket. And that gas leaves the rocket. And that gas leaves the rocket. Full stop. Therefore, the mass of the rocket, decreases with the time. Therefore, the mass of the rocket decreases with the time. Mass of the rocket decreases with the time. Because fuel is burned, it is converted into hot gas, and that gas is pushed away from the rocket. So mass of the rocket decreases with the time. Full stop. According to F equals ma equation, the acceleration should be increased. Acceleration should be increased because the force remains unchanged. Right? Somebody unmute the mic and read that answer. If you have not completely written, I can help you. Somebody unmute the mic and read there.
When the fuel is burned, it is converted into hot gas and that gas leaves the rocket. Therefore, the mass of the rocket decreases with the time. According to F equals ma equation, the acceleration should be increased because the force remains unchanged.
Very good. Thank you very much, dear. Listen, dear. Now I can explain the story. If you would like, I can give a simple numerical example and explain. Listen, dear. So let's say rocket is in the space. So gravitation attraction force of the Earth is now not acting on the rocket. Let's say it is far away from the Earth. So now let's apply F equals ma equation, right? The force given by the engine of the rocket, as I remember, it was 3 into 10 to the power 7 Newton. Am I right, dear? Somebody please tell me. I think it's correct, right?
Yes, sir.
Mass of the rocket, earlier it was 2 into 10 to the power 6, as I remember, 10 to the power 6. The acceleration is 8. So let's say this is a situation somewhere in space. Now let's say mass is reduced. When it was leaving the Earth, it has a mass of 2 into 10 to the power 6. Now let's say its mass is 1 into 10 to the power 6, and it is far away from the Earth. Therefore, gravity of the Earth is not acting, right? But force remains unchanged. So the easiest method is, I have asked you to write this 3 into 10 to the power 6, 7 as 30 into 10 to the power 6. Why did I ask you to write like that, dear? Because then we can cancel out this 10 to the power 6 of mass. Am I right? So what is the acceleration? Yes, so under this imaginary situation, what is the acceleration of the rocket, dear? 10 to the power 6 and this 10 to the power 6 cancelled out. So what is the acceleration, Lamai? Hello? What is the acceleration under this condition?
So 30 meters per square
30
second.
meters per square
30
second, sir.
meter per second. Yes, 30 meter per square seconds, right? So what is the situation? I am considering a situation. The rocket is at far away from the Earth, right? Now the mass of the rocket is 1 into 10 to the power 6. So I just apply F equals ma. The only force acting on the rocket is the force generated by its engine. So now it is 30 meter per square second. It's a large acceleration. And we wait for some more time. We wait for some more time. And right now mass is further reduced. Mass of the rocket is further reduced. Right? Now let's say mass of the rocket is, now again I'm going to apply F equals ma equation. Right? Mass of the rocket is now, let's say, force remains unchanged. It is 3 into 10 to the power 7. Force remains unchanged, but mass is now reduced, let's say 0.25 into 10 to the power 6. So what has happened to the mass there? Mass is reduced. I'm really happy when students ask this kind of questions, right? Can you explain again? Because I didn't understand, we didn't understand how the acceleration changed. Right now, as usual, I write this 3 into 10 to the power 7 as 30 into 10 to the power 6, right? And 0.25, simple maths. Maths people, how do we write 10 to the power 0.25 in mathematical calculations there? 10 to the power
25 over 100.
Yeah, you can write yes, 25 over 100. Or can't we
1 over
write
4, sir.
1 over 4? What do you think about 1 over 4? Correct or wrong?
Correct, sir.
sir.
Sir,
Correct,
1 over
correct.
4.
So for the in the place of 0.25, you can write 25 over 100 or 1 over 4 and 10 to the power 6 into 8. Now what will happen here? This 10 to the power 6 and this 10 to the power 6 cancelled out. So what are the remaining terms there? This 4 will be there, this 30 will be there. So then look at board very carefully. Then we have, then the remaining terms will be 30 this side, and the other side we have, this side we have 30. At the other side we have 1 over 4. 1 over 4 into acceleration. So what should I do next step there? I can take this 4 to the side of 30. I can take this 4 to the side of 30. So then it will be 30 into 4 equals, if you want, you can write 1 into a. You can write, yes, 1 into a. So what is the acceleration now? Lamai, what is the acceleration now?
120 meters per
120
second.
meters per square
30
second.
times 4. 30 times 4 means 120. So what has happened to the acceleration then?
Increase.
Acceleration has been increased. But has the force been reduced? Is force reduced or remains unchanged?
Remains unchanged, sir.
Force remains unchanged, but the mass of the rocket has been reduced. Therefore, the acceleration is increased. So this is the story. So I would like if you write this calculation saying a note. Saying a note, please write this calculation. It will help you to understand this question in future. If you read this question in future, this note will help you to understand. So please quickly write it. The only thing is the mass here, it was 1 into 10 to the power 6. After some more time, mass is reduced to 0.25 into 10 to the power 6. So as the mass is reduced, as the force remains unchanged, so acceleration increases. Yeah, I explained it, right? Students ask, why don't we subtract mg Can somebody tell me why didn't we subtract mg? Why didn't we use the mg term? Somebody unmute the mic and tell.
Sir,
Because we are far away from the.
Dear, please again tell me the answer. Lamai, why didn't we use mg? Your answer is correct, but I didn't hear it properly. Please slowly and loudly tell me why we didn't use mg here.
sir, because we are far away from the Earth and gravitational acceleration acts no more on the rocket.
Very good, excellent. Because I have clearly said that the rocket is far away from the Earth. So I am considering a place where a rocket is far away from the Earth, and now gravitation mg force is not acting. But is it wrong if the Earth is closer to the Earth there? Is this calculation is wrong if the rocket is closer to the Earth?
Yes, sir.
No. Still, whether rocket is closer to the Earth or not, this calculation is clear. Then I just want to reduce the simplification steps here. That's why I reduce mg. That's why I have used an imaginary situation saying rocket is at far away from the Earth. But even it is closer to the Earth, same calculation will be there. Same theory, same logic can be applied. The only thing is calculation will be somewhat difficult. It means steps, we will have more steps. But the acceleration will still be increased. Acceleration will still be increased even even rocket is closer to the Earth. Okay, dear. I just wanted to give you a, I just wanted to do a simple simplification, right? To skip mg term, I have said that rocket is at far away from the Earth. But even it is closer to the Earth, mg term will be there. But due to the reduction of mass, acceleration will definitely be increased. Even it is very closer to the Earth. It's not a problem. Okay, dear. Is it clear, or may I again explain? Lamai?
Clear, sir.
Right. Thank you. If you have any further doubt, just send me a message. Send a message Zoom chat if you want any further explanations. So please tell me once you have written them, okay? Once you have written these things, please tell me, then I can go to the next question. Send a message to Zoom chat saying done. Then I'll go to the next part of the question. Right. Let's go to the next question. if the rocket is closer to the Earth, you cannot neglect mg, right? The rocket should be very far away from the Earth, then only you can neglect mg. Otherwise you can't. Right, so I'll erase these things. If you want, please take a screenshot, because I want to go to the next part of the question. Right, the next part of the question is sketch. You see, sketch the velocity time curve for the shuttle for the corresponding situation. So we should draw velocity time graph under this condition. So what is the condition? What is the situation here, dear? Corresponding to the situation described in Roman number 7. Situation described in Roman number 7. In Roman number 7, it is we have said that acceleration increases with the time. Right. So we should draw the velocity time graph. So this is the time axis. This is the velocity axis. Somebody please tell me what should be the velocity time graph if the acceleration is constant. Somebody. Lamai. It's a Lamai.
The velocity will
Sir,
increase
straight
with
line.
time.
It's a straight line. Very good.
What?
It's a straight line. If the acceleration is constant, it should be a straight line. But is the acceleration constant here? Is it constant here?
No, sir.
It's not constant. So as the acceleration is not constant, it is not a straight line. It will be a curve like this. So I just have drawn a circle. Oh, it will be a curve, and unfortunately I can't rotate it. So it's not a circle. It should be a curve like this. A smooth curve. It's somewhat difficult to me for me to draw using a computer. It should be a smooth curve, right? Upward curve. Acceleration increases with the time. That's why it became a curve. If it is a constant acceleration, the graph will be a straight line like this. Got it? But acceleration increases with the time, so it's a curve. Got it? Draw it here. This is the graph for Roman number 8. A student asked me about escape system, and yeah, that kind of thing, that is just electronic there. That's electronic and safety. So many safety systems are there, right? So if that's a pilot in, if that's for the astronauts, for them to be escaped when there is a explosion or anything happens to the shuttle, there's escape systems. Different escape systems are there. Especially in SpaceX, they have developed a very interesting escape system. If you watch their videos, you can watch them. Elon Musk, right? So autopiloting systems are always with the rockets there. Autopiloting systems are always equipped with the shuttles, because you see, you have heard that so many rovers landed on the Mars, but no human has ever traveled to the Mars. So it means all of them travel by autonomous systems there. Yes, no magic, right? And for when a rocket travels to Mars, we don't want any escape system, because no humans travel so far, and still no shuttle travels from Earth to the Mars. I confused with your question now, but I think your question is clear to me, and I think my question is clear to you. Yes, my answer is clear to you. Thank you. And your question was clear to me. Good. So that's the story. Right, shall we go to the next part of the question here?
Okay, sir.
Right, so I'll erase. Actually, the space is very interesting thing there. Very interesting thing. And I hope as you learn in English medium and as you know the international language, yeah, one day you will get the chance to travel in space. Not to travel, but also to work in space, yes. Right. That is possible here. Because Sri Lankans have that kind of good abilities. One day they will work on moon as well as on the Mars. Right, Roman number 9. Consider a situation where the shuttle is moving horizontally closer to the Earth. Now they say it is closer to the Earth. Horizontally and closer to the Earth. Moving horizontally and closer to the Earth. As shown in the figure, with the velocity of 4 into 10 to the power 2. 4 into 10 to the power 2 means 10 to the power 2 means 100. 4 into 10 to the power 2 means 400. The mass of the shuttle at this instant is 1 into 10 to the power 5. Why the mass is reduced here? Because it has traveled, its fuel is burned, so its mass is reduced. So they tell us a story. Unfortunately, due to an external explosion, the shuttle breaks into 2 pieces, P and Q. The shuttle breaks into 2 pieces, P and Q, with equal masses. That's the point. If the mass of one piece is M, the mass of the other piece should also be M. If the piece P move forward horizontally, if the piece P move forward horizontally with the velocity of 8 into 10 to the power 2 relative to the Earth, as shown in figure B, determine the velocity of Q relative to the Earth. So here in my figure, they have not marked this P and Q pieces, but in the examination figure, this is an edited figure given by one of our typists, right? So the P means this piece. The front piece was named as P. The other one, this was named as Q, right? So you have to draw a rough sketch of this figure quickly. So Q is this one, P is the front one, right? And this is the shuttle. Now, listen to me. If the mass of this piece, if the mass of the piece Q is M kilogram, listen to me carefully. If the mass of this piece is M kilogram, what is the mass of the other piece here? Somebody unmute the mic and tell me. Mass of this one. That should also be M kilogram. That should also be M kilogram, because question tells that the rocket is broken into 2 equal pieces. Mass of this one is P. Mass of this is M. Mass of this is M. Then what should be the mass of the rocket before the explosion there? Total mass of the rocket.
2m, sir.
It should be 2m. So if the mass of the rocket is 2m kilogram, once it is broken into 2 equal pieces, mass of one piece will be m, mass of the other piece will also be m kilogram. Can you draw a rough sketch of this figure here? Rough sketch of this figure. Here, this figure shows this one. It shows the before the explosion. This shows before the explosion. Before the explosion, right? The other figure shows after the explosion, or let's say just after the explosion. Just after the explosion, right? And just draw a rough sketch of this figure and let me mark the velocities. Velocity of the rocket before the explosion is 4 into 10 to the power 2 means 400 meter per second. And the velocity of this piece, velocity of the piece Q after the explosion, let me take it as V1. We don't know what it is. We don't know what it is. That's the question of yes here. And velocity of the piece P after the explosion, that is, let me mark it as V2. It is given as 8 into 10 to the power 2. 8 into 10 to the power 2. So that is 800 meters per second, right? Let me mark the directions also. I just mark directions as I wish. So rocket was moving horizontally into my right hand side. So after the explosion, I think that P moves to my right hand side, and if I want, I can mark V1 into the opposite direction. Normally, due to an explosion, the two pieces should start to move into the opposite directions. If our directions are correct, we will get positive answers, positive answer for V1. If the direction is wrong, we will get a negative answer for V2. So if we get a negative answer for V2, we should understand that V1. If we get a negative answer for V1, we should recognize that, we should identify that rocket piece Q is moving to the opposite direction. So if we get a negative answer, we will consider it about that. Right, draw the figure here, quick. And send a message saying done once you have drawn the figures. Figure 1 shows the situation before the collision. Figure 2 shows the situation just after the collision. I have marked the velocities after the collision as V1 and V2. V2 is given as 800 meters per second. P and Q were marked on the original figure. So I have taken mass of one piece as M, mass of the other piece as M. So M plus M is 2M. Therefore, the total mass of the rocket should be 2M kilograms. Got it? Draw the figures, mark the directions, mark the velocities, masses, and name them as P and Q. Once we have finished drawing, send me a message saying done. Then I'll go to the next part. Start. And the other thing is, all these velocities are marked relative to the Earth, right? V1, V2, 400, all of them are marked relative to the Earth. Right. Now, what is the theory? What's the law that should be used to find the velocity of this piece Q after the explosion? Somebody unmute the mic and tell me.
So the law of linear momentum.
Very good. So for the simple equation to find the velocity of the piece Q after the collision, we should use the law of conservation. The law of conservation of linear momentum. The law of conservation of linear momentum should be applied. The law of conservation of linear momentum tells us total linear momentum not change. It means if the total linear momentum is not changed, initial total linear momentum, let me use the letters L and M for linear momentum, should be equal to the final total linear momentum. But here we must select a direction, because linear momentum is a vector. Linear momentum is a vector, therefore we must indicate a direction. So as objects are moving to the right hand side, so I'll take the direction of linear momentum into this side. So this is the direction that I use. Right. So let's continue. So initial total linear momentum means initially there is rocket. Mass of the rocket is 2m. Its velocity is into our direction, that is 400. Final linear momentum. Finally, how many pieces are there? Finally, how many pieces are there? After the explosion, how many pieces of the rocket are there?
Two, sir.
Two
Two
pieces.
pieces are there. Mass of the first piece is simple m. Its velocity is v1. So direction of our equation, all the things are moving right hand side, but q is moving into the left hand side. So when we work with vectors, we must use a minus sign to indicate the opposite direction of v1. Got it here? Why did I put a minus sign with v1? Lamai? Why did I use a minus sign with the velocity v1?
Because
The direction of the velocity v1 is into the opposite direction of the equation. I have applied the equation into the right hand side. It means the direction of 400, direction of v2. So as the direction of v1 is opposite to the direction of the equation, I should use a minus sign. Mass of the piece q is simple m. Its velocity, it's not a problem. It is 800. So what is the next simplest thing that can be done here? That's a very simple thing that can be done next as the next step. To see that this m, and this m, all the m terms can be cancelled out. So what are the remaining terms then? Here we have 2 into 400 equals, here we have minus v1, minus v1, minus v1, here minus v1, and here we have plus 800. So what should I do next here? What should I do next? 2 times 400 is, Lamai?
800.
800, sir.
Equals minus v1 plus 800. So what should I do next here? I can take this minus v1 to the other side. This minus v1 can be taken to the other side. Then minus v1 will be, Lamai?
Plus V1.
Plus v1 equals 800 is there. What about this 800 here? This 800 goes to the other side as
minus 800.
this 800 goes to the other side as minus 800. Then what is plus 800 minus 800? What's the answer?
0.
So it means what is the velocity of the piece q after the explosion?
0 meters per second.
0 meter per second. Please write this here. So this is the complete answer. Write it. Student asked whether it is possible for the rocket to move faster than the velocity of exhaust velocity. That is impossible, because even this question, it is confirmed. Velocity of the rocket is 150. Velocity of the gas relative to the earth is 9,850. So velocity of gas is very much greater than, very much larger than the velocity of the rocket. The reason is mass of the gas created per second is 3,000 kilograms. But mass of the rocket is 2 into 10 to the power 6. It means how many kilograms, dear? So mass of the rocket is very much larger than the mass of the gas created per second. Therefore, velocity of the rocket is smaller than the velocity of the exhaust gas. Mass of the gas is 3,000 kilograms if we consider 1 second. But mass of the rocket is 2 into 10 to the power 6. Very much greater. So more mass means less velocity. So a rocket cannot have a larger velocity than the exhaust velocity of the exhaust gas. Is it clear here, Lamai?
Yes, sir.
Right. The simple B equation. What do you think about simple B, dear? Can somebody read simple B equation?
What is the velocity of q relative to p?
So how do you find it here? Velocity of Q relative to the P. P and Q are moving along the same path into the opposite directions. Therefore, what is the relative velocity?
Summation of the two velocity.
Very good. So simple. Velocity, we don't write that sentence. Velocity of Q relative to P. Velocity of Q relative to P means if there is a person on P, if he is looking at Q, as he observe, what will be the velocity of Q? For example, here, when we travel in a bus or a vehicle, we observe that coconut trees are moving. Do they really move in here? Lamai? Do coconut trees really moving?
No, sir.
No, they are not really moving, but we observe as they are moving, right? So like that, if a person is on P, he will observe that Q is moving. Another simple idea of relative velocity. So P and Q are moving along the same path into the opposite directions. Therefore, the relative velocity is just summation of V1 and V2, their velocities. So what is V1 there? We have found V1 as Lamai.
0.
0, sir.
What is V2?
800 meters per
800
second.
meters per second.
You see the upside here. You see the upside here. 0 plus 800 is 800. See the upside. Actually, who is moving? Lamai, actually, who is moving?
P.
Actually,
P is moving, sir.
Actually, P is moving, yes. But if a person is on the piece P, he will say, I am not moving. Q is moving with the velocity of 800. You see it? You see the beauty? And he will give a direction. He will say the piece P is moving 800 meters per second away from me. He will give a direction like this. See the beauty? So that's the nature here. Even we are doing wrong things, we feel that we are right and other people are wrong. Am I right there? Hello? Actually, we are wrong.
Yes, sir.
Yes, sir.
Exactly.
Actually, we
sir.
are wrong. Yes, dear. Yes. Actually, we are wrong, but we feel that we are right and other people are wrong. So that's the nature of universe here. You see, actually P is moving, but if a person is on the P, he will say gap between P and Q increases by 800 meters per second. That's the meaning of this 800 meters per second. For each and every second, gap between P and Q increases by 800 meters. So he will say, he will really observe, actually he is not thinking. He really observed that the piece Q is moving away from him. Like we observe the coconut trees are moving when we are traveling in a vehicle. Same thing happens here. So he will say, piece Q is moving away from me with the velocity of 800 meters per second into this direction, into the direction that I have marked. Moving away, moving away main direction should be to that side. So may I take 2 more minutes and complete the question there? Are you tired? Give me the permission quick.
Okay, sir.
Okay, sir.
Right. So that will be the end of the question. Just give me 2 minutes. Right. If you want, please take a screenshot. I'll erase because I'm going to erase everything. As I'm going to erase everything, if you want, please take a screenshot. Right. Now let's move to the other question. Right. A completed, B completed, C. Right. Can somebody unmute the mic and read simple C question? Somebody in the class? Can somebody read simple C?
Subsequent motion of pieces P and Q after the explosion as seen by an observer on the earth.
If a person on the earth, how will he observe these pieces there? Let's say there is a person on the earth and he is looking on these objects. So what will he tell us there? What is the velocity of Q? Velocity of Q is 0. So it means he will tell us the P is Q falling downward freely under the gravity. And what about P? Because the Q will fall freely under the gravity, right? So along a straight line like this. It is somewhat difficult for me to draw. It is falling freely under the gravity along a straight line like this. Q has a velocity of 800 meters per second. Therefore, Q will be moved along a curved path, and it will be attracted to the earth due to the gravity of the earth. So it will be moved in a curved path like this and hit on the earth. So motion of P will be a projectile, very similar to a projectile. Got it here? So it's better if you draw this figure, and below the whether you draw the figure or not, it's not a problem. But if you draw this figure, you can understand it much easier. So just draw the figure. After that, we should say P's Q will fall freely under the gravity vertically downward. P's Q falls freely under the gravity. Along a vertical straight path. P will be moved along a curved path similar to a projectile. This should be a curve. I don't think I have drawn a better curve, but it is a curve. So what's the answer? Q falls freely under the gravity along a vertical straight line path. P will be moved along a curved path similar to a projectile. Something like this. Right, so that's it. Would like if I explain the story, because you should remember that they are moving closer to the Earth's surface, right? If you read the question, it is clearly said that they are moving closer to the Earth. As they are moving closer to the Earth, the gravity of the Earth pulls them downward. Right. Got it? Q falls freely under the, listen carefully. Q falls freely under the gravity along a straight line path. Q falls freely under the gravity along a vertical straight line path. Q falls freely under the gravity along a vertical straight line path. P moves along a curved path similar to a projectile. P moves along a curved path similar to a projectile. I ask you to draw this figure not to earn marks, but it will help you to recall your memory when you read this question again. That's why I have asked you to draw the figure. Somebody in the class, please repeat the answer. Somebody please read the answer again. It will be a big help for the students. Okay, I'll read because nobody read the note. Q falls freely under the gravity along a vertical straight line path. P moves along a curved path similar to a projectile. Right. Now let's go to simple D equation. That's the end of the question. Yes. Yeah. So simple D equation. If the explosion lasts, I'm going to erase everything. If you want, take a screenshot. If the explosion lasts for 0.2 seconds, what is the average value of the force exerted on each piece due to the explosion? If the explosion lasts for 0.2 seconds, what is the average value of the force exerted on each piece due to the explosion? Very simple, dear. Listen. So if we go back to the original figure again, right? Listen, dear. Masses are given. As I remember, yeah, some masses are given. Listen. So this rocket is moving. Initially, it is moving with the velocity of, let me take it as u. Initially, it is moving with the velocity of 400 meters per second. Both pieces as a single object. I can mark the direction later. After the explosion, the piece Q, velocity V1 becomes 0. Piece P start to move with the velocity of, let me take it as V2, with the velocity of 800 meters per second. 800 meters per second, right? So mass of this one is, I have taken mass of this piece as m kilogram. Actually, this value is given, m kilogram. And mass of the other piece is also m kilogram. Right. So if the mass of one piece is m, the mass of the other piece is m, the total mass of this should be 2m. The total mass of this should be 2m. Right, but I would like to draw them separately. Just before the collision, mass of this one m kilogram, right? M kilogram. Right, and mass of this one is also m kilogram. I'll draw them just considering just before the collision, going to be broken. Right, I'll draw a line to indicate the two pieces separately. Mass of this P is this piece is P M. Mass of the other piece also M. So I'll keep them like this. Now you should understand this point clearly. So let me draw a dotted line to indicate the two pieces. So let's say they are broken from this point. But still they are moving together as a single object, but just within less than 1 nanosecond they are broken. So this explosion is something like this here. This explosion, during the explosion, the piece P, the piece Q give a force to Q gives a force to P. This is Q. This is Q. It gives a force to P. According to Newton's third law of motion, right? According to Newton's third law of motion, the piece P should give equal and opposite force. Equal and opposite force. So the piece P will give another force into this direction. Can you understand it? Right? Would you please draw this figure quickly? Please quickly draw this figure. After that, I'll explain. I just want 2 more minutes to finish this one. Right. So I have used green color for piece P, and I use green color for the force given by the piece P. I have used red color for the piece Q. I have used red color for the force given by Q. Right. So these forces are equal in magnitude, opposite in the direction. Please draw this figure, roughly draw this figure, right? No need draw a beautiful, nice space shuttle, right? Just draw a rough figure and mark the given forces. So, for me to explain easily, I'll mark this as F1 Newton. So F1 Newton is the force given by Q to P. And F2 Newton is the force given by P to Q. Even I have marked them as F1 and F2, they are equal in magnitude. If F1 is 100 Newton, F2 is also 100 Newton. Equal in magnitude, just opposite in the directions. Got it? Even though I have used two different colors and two different values as F1, F2, they are equal. Right. So who gives this F1 force here? F1 is the force. F1 is, I use red color for F1. You can understand. F1 is the force given by Q to P during the explosion. Got it? Then, right, F2, I'll use green color for it. F2 is the force given by P to Q during the explosion, right? And F1 and F2 are equal in magnitude. F1 and F2. F1 and F2 are equal in magnitude. Are equal in magnitude and opposite in the directions. Whose law is this? Newton's third law of motion. When P gives a force to Q, Q gives the same force to P. Got it? Are you okay up to this point, dear Lamai? Raise your hands up if you are okay up to this point. Right. So after that, I'll do a very, very simple thing. So only to P, I apply the equation F equals ma. The force acting on P is F1 equal its mass. Somebody unmute the mic and tell me the mass of the total rocket. The mass of the entire rocket is given under this situation. I don't remember it. Is it 1 into 10 to the power 5? Somebody?
Yes, sir.
It is 1 into 10 to the power 5, right? So if the mass of the rocket is 1 into 10 to the power 5, if the mass of the rocket is 1 into 10 to the power 5, right? What should be the mass of the P is P, dear? Should be half, neither, because it is broken in two equal pieces. If the mass of the entire shuttle is 1 into 10 to the power 5, half of its mass is P, half is Q. Therefore, mass of P should be 1 into 10 to the power 5 divided by 2. Acceleration is A. So then we can easily calculate what is acceleration actually. Acceleration is change in velocity divided by time taken. Am I right? Acceleration is change in velocity divided by time taken. So velocity of the piece after the collision is v2. Velocity of the piece p before the collision is u. U is 400. And time taken for this is given as 0.2. Or you can use FT equation by considering impulse. That is also okay. If you want, you can use impulse equation to calculate. It's also okay. So 1 into 10 to the power 5 means 10 to the power 5. 1 into 10 to the power 5 means 10 to the power 5. Divided by 2. Divided by 2. Multiplied by V1. What is V1, dear? Somebody please tell me. V2. What is V2? What is V2, dear? If you give me the
800 meters per second.
Yes, per second, sir.
800 meter per second. What is U?
400 meter per second, sir.
100. Before the collision, both P and Q had the same velocity. Just before the collision, both P and Q had the same velocity. So this is just 0.2. So then nothing will happen to this 10 to the power 5. Nothing will happen to this 10 to the power 5. 800 minus 400 here.
400, sir.
200. 10 to the power 5 remains as it is. Not 200, 400 neither.
400, sir.
Yeah, yes. That is 400. This 2 will be there, isn't it? This 2 will be there. 0.2 can be written as 2 into 10 to the power minus 1. Am I right here?
Yes, sir.
We can write 0.2 as 2 into 10 to the power minus 1. Now we can easily solve this problem. Look at both. What is 400 divided by this 2? 400 divided by
200, sir.
200. Right? Nothing will happen to 10 to the power 5. It remains unchanged. 400 divided by 2 is 200. 200. 10 to the power minus 1. This 10 to the power minus 1, this, it will comes up as 10 to the power, Lamai?
10 to the power plus 1, sir. 10.
10 to the power plus 1. And this denominator 2 will be there. It is not changed. The denominator 2 remains unchanged. That will be there. Now, what is the final answer? 200 divided by 2, Lamai? 10 to the power
100, sir.
Yes, very good. 10 to the power 5 will be there. Into 200 divided by 2, 100. 10 to the power 1 means 10. So all together, how many zeros are there? All together, how many zeros are there? Lamai?
10 to power 8.
10 to the power 8. So finally, we get that force acted on the piece P is 10 to the power 8 unit is Newton. If the force acted on the piece P is 10 to the power 8, what will be the force acted on the piece Q? Somebody please tell me.
So it is equal.
Equal, sir.
10 to the power 8 Newton, right? So if you have written them all, now you can leave the class. And I'll wait until all the students write the answers. And I'll wait. If you have any further doubts, I can help you. So if you think, if you want, you can apply the impulse equation. If T equals mv minus m times v minus u. But even this is okay. Actually, the same equation is written here. If you have any further doubts, you can ask, or you can send me a message to my WhatsApp. I think everybody knows my WhatsApp number, or you can send a message to my class admin. They will help you. If you send a message to class admin, they will help you. They will give my number also. Right. So you write them all, and then you can leave the class. And if you have any other class just after my class, you may take a screenshot and leave the class. Even after the class, if you have any further doubt, you can ask. Even now I am here. You can unmute the mic and ask or send a message to Zoom chat. I am always here for you. Good luck.
Thank you, sir. Goodbye, sir.
Luck, dear.
Thank you, sir.
Right. Welcome. Good luck.